Welcome back to the Deep Dive. It is January 16th, 2026. And we'll start today by asking you, just look at your calendar. We are 2 weeks into the new year, and if you've been tracking the Archie feeds or, looking at the internal deployment logs at your company, you might be noticing a shift.
Yeah.
The vibe has changed.
It really has. If we look back at 2024, 2025, the dominant narrative was
Right.
it was just scale.
Right.
It was this relentless drumbeat of make it bigger, add more parameters, throw more compute at the training run, feed it the entire internet twice. And, it worked.
It did.
We got these massive sort of godlike brains.
But now it feels like we're waking up with a bit of a hangover. We built these Ferrari engines, but we're realizing we're trying to use them to deliver pizzas in rush hour traffic.
That is the perfect analogy.
They're powerful, absolutely.
Yeah.
But they overheat, they guzzle gas, meaning money, and occasionally they just drive straight into a wall because they're too confident to check their blind spots.
That is exactly what this week's research stack is addressing. We're looking at papers released between January 10th and the 16th, and the theme isn't about raw IQ anymore. The industry has kind of hit a wall where capability is high, but usability
is actually quite low.
Yeah, exactly.
It's the difference between a research demo and a product.
It is. The new frontier is about making these massive brains actually work in the real world. We're talking about making them cheap enough to run so you don't go bankrupt, stable enough to trust with a sequence of actions, and honest enough, and this is the big one, to tell us when they have no idea what they're talking about.
We have a lot to get through, but I want to frame this entire deep dive around a central tension that just keeps popping up in the literature.
Okay.
It's the battle between reasoning quality and inference cost.
The classic trade-off. It is, I think, the defining economic problem of AI right now.
Let's unpack that. We know the chain of thought works. If you ask a model to think step by step, it gets smarter. It solves harder math problems, it writes better code, it creates better plans. But here's the problem. In a production environment, that thinking is basically a tax.
It is a tax on your budget and a tax on time. You have to remember, every step of that reasoning generates tokens.
And every token costs money.
And every token takes milliseconds to generate.
Milliseconds add up.
They do. If you have a chat bot, maybe a user can wait 3 seconds. But imagine a robot arm on an assembly line trying to catch a moving object.
Or a high-frequency trading bot.
Exactly. You cannot afford to have the model sit there and write a 3-paragraph essay on how it plans to move its arm before it actually moves.
It's the thinking pause that just kills the utility. So the mission for today is to look at the solutions. We're going to look at how to make agents think fast without getting stupid. We're going to look at how to stop agents from spiraling out of control after one bad decision. And we're going to ask the uncomfortable question. When a model says, "I'm sure," is it lying?
That last one is a bit of a horror story, but we'll get there.
Let's dive into the first section then, the cost of thinking. We have a paper here titled Fast Think Act. This focuses specifically on vision language action models, or VLAs.
Right, the brains behind robots.
The brains behind robots.
This is a critical area. VLA models are the bridge between the digital brain and the physical world. They have to see, understand, and then do.
And traditionally, to do a complex task, the model generates just a massive text trace.
A huge one.
Right. So if I tell a robot, clean up that spilled coffee, the model internally goes, I see a spill. I need a sponge. I need to move my arm to the sponge. I need to grasp it. All these words.
Exactly. That is explicit chain of thought. And while the robot is generating all those words internally, it's just freezing. It's lagging.
And in the physical world, lag is dangerous.
It's a deal breaker. So what does Fast Think Act propose? They use a term called verbalizable latent planning.
Okay, that sounds incredibly technical. Break that down for us.
To understand this, I want you to think about how you learn to do long division, or maybe solve a complex math proof in school. When you're a student, what does the teacher make you do?
Show my work. Every single step.
Every single step? First I move X here, then I divide by Y. That is explicit chain of thought. It's slow, it's verbose.
Painful.
But it ensures you don't skip a logical step. But now think about a mathematics professor or, a genius-level mathematician. Do they write out every single micro step?
No. They just look at the equation, their brain does this massive amount of processing, and they just They write down the answer.
Yeah.
Or maybe one intermediate step and then the answer.
Exactly. That background processing that happens in the expert's brain, the stuff that isn't spoken out loud or written down, that is latent reasoning. It's intuition born from experience.
So Fast Think Act is trying to turn the model from the student who needs to show their work into the expert who just sees the path.
Precisely. They're distilling the heavy, token-based planning of a teacher model into a compact, latent representation in the student model.
A compressed thought.
A compressed thought. Instead of generating hundreds of words of planning text, the model generates a compressed vector, a mathematical fingerprint of the plan, and then acts immediately.
It's compressing the thought. And the numbers in the paper are wild. They claim an 89.3% reduction in inference latency.
Which is massive. I mean, that is the difference between a robot pausing for 10 seconds to think versus moving almost instantly.
It makes the difference between a robot that's a novelty and a robot that's actually useful.
All right.
But there's a really important word in that title we kind of skipped over, verbalizable.
Yes. This is crucial for safety.
Because usually when we talk about latent space or vectors, we're talking about a black box.
A total black box.
If the robot decides to throw the coffee cup at the wall instead of cleaning it, and made that decision using a latent vector, we usually have zero way of knowing why.
Right. We can't read the vector. It's just a string of numbers. But Fast Think Act is designed so that the latent thought can still be decoded.
So even though it thinks in silence to save time, we can pause it and say, hey, explain yourself.
Exactly. We can force it to translate that compressed vector back into English text for debugging. It's like asking the math genius, wait, how did you get that? And they can stop and explain the steps if they absolutely have to.
That feels like the best of both worlds.
Yeah.
You get the speed of intuition, but you keep the accountability of the step-by-step logic.
It really shifts thinking from being a runtime cost, something you pay for every single time the robot moves, to a training conceptual choice.
You pay up front.
You pay the cost up front to train the intuition so you can move fast later.
Okay, so that's how we handle robots. But what about pure text reasoning? Because there's another paper in this stack, Distribution-Aligned Sequence Distillation, that's tackling the same problem, making small models smart, but from a totally different angle.
Right. This is for when you want a smaller, cheaper model, say a 7 billion parameter model to reason, as well as a massive 70 billion parameter monster.
Okay.
And usually we use something called supervised fine-tuning, or SFT.
Which is basically showing the small model the big model's homework and saying, copy this.
Pretty much. We take the best answers from the teacher model and feed them to the student. But there's a massive failure mode here that we're just starting to understand. It creates what's called exposure bias.
Exposure bias. What does that look like in practice?
It means the small model learns to parrot the answer, but it doesn't understand the mindset behind it. It's like a student who memorizes the answers to the practice test.
Oh, okay.
They get 100% on the practice, but then they sit for the real exam, and the questions are phrased slightly differently, or they require a slightly different logical leap.
And the student fails completely. Because they didn't actually learn the logic, they just learned the pattern of the answer.
Exactly. The model suffers from collapse on long reasoning chains. It starts strong, but then it just drifts. It loses the thread because it hasn't learned the full probability distribution of how the teacher thinks.
It knows the words, but not the flow.
The music behind the words, yes. So how does distribution-aligned sequence distillation fix this?
Yeah, what's the trick?
It's a bit technical, but the core idea is brilliant. Instead of just minimizing the difference between the final text outputs, this method aligns the full output distribution.
Okay, let's break that down. What does that mean, the full distribution?
It forces the student model to understand the probability of different reasoning paths. It's not just learning the answer is B, it's learning there's a 60% chance the reasoning goes down path A and a 40% chance it goes down path B, and both eventually lead to the conclusion.
So it's capturing the nuance. It's capturing the uncertainty and the branching nature of the teacher's thought process.
Yes. It is cloning the teacher's uncertainty and confidence, not just the text. And the efficiency is startling. They achieved competitive results with only 448,000 training samples.
Which, for listeners who don't train models, is tiny.
It's nothing.
Usually we're talking about millions or billions of tokens.
It's an order of magnitude less data for a much more robust result. So if we synthesize this section, Fast Think Act gives us speed by compressing the thought into a vector. And distribution alignment gives us quality by making sure the small model actually understands the texture of the reasoning, not just the words.
So we're getting better at packaging intelligence into smaller, faster containers.
Yeah.
But, and there is always a but,
Of course.
intelligence is useless if the agent goes crazy.
Ah, the stability problem.
I call this the house of cards issue. We're all excited about agents AI that can use tools, book flights, manage calendars. But anyone who has built one knows they are incredibly fragile.
Incredibly. So true.
You build an agent to do a 3-step task, get the weather, pick an outfit from a database, and email me the suggestion.
Okay.
If it makes one tiny mistake in step 1, maybe it grabs the weather for the wrong city, everything that follows is technically logical. It picks the right outfit for that weather. It writes a perfect email. But the whole thing is wrong because the premise derailed.
This is the curse of sequential decision-making. We call it trajectory instability. Agents usually suffer from myopic step selection.
They're short-sighted.
They look at their feet. They ask, what is the most likely next word? Or what is the most obvious tool to call right now? They don't look at the horizon. They don't consider if the action they're taking is robust enough to support the rest of the plan.
This brings us to the paper Max Metadaptive Exploration. This feels like a direct response to that fragility.
It is. MacXS is trying to bridge the gap between simple text generation and actual search algorithms, like the ones used in chess computers. It introduces a sanity check loop into the agent's brain.
Walk us through this. Let's use that flight booking example.
Yeah.
The agent is about to select a date. It's hovering over the Monday button. What does MacS do?
Before it actually clicks that button or sends that API call, it performs a look-ahead rollout.
Previews the future.
It simulates a few steps ahead. It asks, if I choose Monday, what happens next? But it doesn't just do it once. This is the stability-aware part. It might run that simulation 5 times to check for consistency. Because these models are probabilistic, sometimes they hallucinate or make errors. If the model runs the simulation 5 times, and 3 times it successfully books the flight, but 2 times it crashes or ends up in a loop of errors, the system flags that step as unstable.
That is really smart. It's basically saying, if I do this, there's a 40% chance I get confused later, so I shouldn't do this.
Exactly. It rejects the step. It forces the model to backtrack and look for a path that is consistent across multiple simulations. It's searching for consensus within its own imagination.
But wait, playing devil's advocate here based on our first section, doesn't running 5 simulations for every step make it incredibly slow?
Yeah.
We just spent 10 minutes talking about how we need to be fast.
That is the trade-off. However, MacXS uses a concept called trajectory convergence. It's a dynamic budget.
Okay, how does that work?
It doesn't always run 5 simulations. It starts with 1 or 2.
Yeah.
If the outcomes are identical, if the path is obvious and stable, it stops thinking and executes. It only spends the extra compute time when the path is blurry or risky.
So it's pragmatic, it thinks hard when it's confused, and acts fast when it's sure.
The insight is, if you must search, make the search stable. It prioritizes agent stability as much as agent intelligence. It's admitting that being smart isn't enough if you aren't reliable.
That feels like a massive step toward agents we can actually trust to do work while we sleep. It's checking its own work.
It is. But speaking of trust...
Oh boy, here we go.
This is the part of the deep dive that actually keeps me up at night.
We're moving to the third section, confidence calibration. This is arguably the scariest part of this week's research because it deals with decision-making.
The paper is titled, Are LLM Decisions Faithful to Verbal Confidence? And honestly, if you're a CTO or a product manager or anyone using LLM to make automated decisions, you need to listen to this very carefully.
Let's set the scene. A lot of companies are building systems where the AI is a decision aid. Maybe it's a trading bot deciding to buy stock.
Right.
Maybe it's a medical triage system deciding if a patient needs a doctor.
And the standard logic is, we'll ask the model for its confidence score. If the model says, I am 90% confident, we execute the trade. If it says 40%, we ask a human.
It seems logical. We treat the model like a human expert. If a senior surgeon looks at an X-ray and says, I'm 99% sure this is a fracture, you trust them.
We assume the verbal confidence maps to reality.
Yeah. But this paper asks, does it? Is the model's verbal confidence, that sentence where it says, I am 95% sure, actually connected to its internal probability of being right?
And what they found is It's disturbing. They introduced a framework called risk eval. They basically set up a high-stakes game.
Okay.
The model answers questions, it gets points for being right, and this is key, it gets penalized heavily for being wrong.
So there's a cost to failure. It's not just, oops, it's you lost money.
Exactly. And they set the penalties so high that the mathematically optimal strategy for many questions was to abstain, to just say, I don't know.
To fold your hand.
To fold the hand. Any rational player would look at the risk and say, not worth it, pass.
Right. So what did the models do? I have a sinking feeling.
They almost never abstained, even when the penalty for being wrong was extreme enough to wipe out their entire score. They plowed ahead.
You're kidding.
They would say things like, I'm very confident, and then give the wrong answer.
That is terrifying. It's like a gambler who can't stop betting even when they know the house is rigging the game.
The researchers call it utility collapse. The paper shows a critical dissociation between reasoning and decision-making.
Explain that dissociation. What does that mean?
It means the model might actually know. The answer is shaky. If you looked at the raw token probabilities deep inside the math, it might be uncertain. But the part of the model that generates the decision, the part that speaks, lacks the strategic agency to convert that uncertainty into a stop signal.
So when a model says, I'm sure, it isn't a measurement, it's a performance.
Yes. That is the perfect word for it. It is a performance. It has been trained on millions of documents written by confident humans. It has learned the style of confidence. It mimics the cadence of an expert.
But it doesn't have the internal cost awareness to back it up.
Not at all.
So a model will sound like a confident expert while walking right off a cliff.
And it will take your budget with it.
That is a huge wake-up call. You cannot treat sounds confident as safe to act on.
No. If your production system relies on a verbal confidence threshold, your system is fundamentally flawed right now.
You're building on quicksand.
You really are.
Wow. Okay, we need to solve that. But before we get to the solutions, let's quickly touch on the data side. Because if we can't trust the models to know when they're right, and we can't afford humans to grade them, where does the data come from?
The synthetic frontier.
We have two brief highlights here. First, Xcoder. This is about code generation.
Code is interesting because it's one of the few places where we can solve the confidence problem objectively.
Right.
Xcoder introduces a pipeline called SynthSmith. It generates a coding task, it generates the solution, but crucially, it also generates the test cases.
Why are the test cases the secret sauce?
Because code executes. It either runs or it errors out. Unlike an essay, you can prove it works.
It's black and white.
It is. If the system generates a synthetic task and solution, it can run its own synthetic test case. If the code passes, the data is good. If it fails, it's trash. It closes the loop without a human.
And it scales.
Massively.
Massively.
Then we have Dr. Zero, which, as I've said, sounds like a Bond villain.
It does. Self-evolving search agents without training data.
The promise is a feedback loop, where a proposer agent challenges a solver agent. They spar, they get better.
It's the AlphaGo concept applied to general agents, but I have to admit, I'm a bit skeptical here.
Why?
The paper claims to match supervised agents, which is impressive, but we've seen self-play papers before. The devil is in the details. Is it actually generating novel strategies, or is it just overfitting to its own specific game rules?
Right.
Without seeing more artifacts, we have to wonder if this is a breakthrough or just a really good iterative loop.
Oh, fair enough. Keep the hype in check.
All right. We've covered the cost of thinking, the fragility of agents, the lies of confidence, and the synthetic data pipeline. We're at the point in the deep dive where I ask you to be the filter.
Okay.
Our listener is going back to work on Monday. They have a boss asking for AI features. They have a limited budget. From this stack of papers, what should they actually try this week, and what is just noise?
Let's break it down into the try it pile and the skip it pile.
Start with the actionable stuff. What goes on the whiteboard Monday morning?
First, if you're building anything embodied, robots, drones, or even a very fast chat interface, look at the fast think act concept.
The latent planning.
Yes. Even if you don't use their exact code, the principle is vital. Stop making your agent recite Shakespeare before it acts. Distill your planner into a planned sketch or a latent vector.
Move the heavy lifting.
Move the heavy thinking to training time so the inference is light.
Got it. Speed up the loop. What's next?
Second, for stability. If you have an agent that uses tools, especially if those tools cost money or modify a database, you need the MacXS logic.
The simulation check.
Implement a sanity check loop. Before your agent calls an API, force a short look ahead. Ask the model, simulate the result of this action 3 times.
And if they're all different?
If the outcomes vary wildly, if one time it works and two times it errors, force the agent to stop and ask for help. Do not let it guess.
That feels like a few lines of code that could save a lot of headaches.
Absolutely. And the third one is for everyone. Evaluation. You need to replicate the risk-evil test.
How do they do that?
Take your production prompts, the questions your users actually ask, force your model to answer them, but also ask it to bet points on its answer. See if high confidence actually correlates with high accuracy.
And spoiler alert.
It probably won't. But you need to know how bad the calibration is. You need to measure the gap between its mouth and its brain.
Okay, that is a solid to-do list. Fast planning, sanity checks, and confidence auditing. Now, what about the skip it or wait and see pile?
There are two papers here that are interesting but underspecified. First, FinForge.
The finance benchmark.
It looks promising for evaluation hygiene in finance, which is desperately needed, but the methodology in the paper is currently too thin. We don't know enough about the semi-synthetic nature of the data to trust it as a standard yet.
So don't base your trading strategy on it yet.
Not yet. And the second is Structured Episodic Event Memory. This proposes event frames for long-term memory.
Moving beyond just saving raw chat logs.
Right. It's a great concept, but there's no code and there are no clear benchmarks. It's a cool idea, but right now it's just that, an idea. It's hard to tell if it's a new architecture or just fancy prompting.
So wait until they show their work.
Exactly.
Bringing this all together. What does this week tell us about the trajectory of AI right now?
You know, for a long time, the theme was superintelligence. It was about the singularity, godlike powers, solving physics.
Right.
But looking at this week, the theme is maturity. Yes. We're seeing methods to discipline the models. We're making them efficient with FastThinkAg. We're making them consistent with MacX. And with RiskEval, we're exposing their overconfidence. We aren't just trying to make them bigger anymore. We're trying to make them act like adults.
That is a really powerful framing. We are finally sending the teenager off to military school.
In a way, yes. We're demanding reliability.
And that leads me to a final thought I've been mulling over while listening to you talk about that confidence paper.
What's that?
We spend so much time trying to make models smarter. We want them to know everything. But looking at that risk-eval failure, where the models refused to abstain even when they were wrong, maybe the most valuable trait we're missing isn't intelligence.
What is it?
It's cowardice.
Cowardice. That is provocative.
Think about it. We need models that are smart enough to be afraid of being wrong.
Yeah.
We need them to have that pit in their stomach that says, I shouldn't do this. I don't know enough. Until they learn to say, I don't know. Until they learn that fear of failure. Can we ever really trust them with the keys?
That is a profound point. Intelligence, without doubt, is just delusion. And right now, our models are delusional.
On that cheery note, I want to encourage you, the listener, to pick just one of these concepts, maybe that MacX consistency check, and see if you can break your own agents with it this week. It's better you break them than your customers do.
Absolutely.
Thanks for diving deep with us. We'll see you next time.